Good morning, everyone. Today I will talk about my study, Transient Modulation of Kuroshio Upper Layer Flow by derailing impinging typhoon Morakot in east of Taiwan in 2009. First, I want to talk about why we choose the Kuroshio as the study region. We can see the Kuroshio is a strong western boundary current passing east of Taiwan throughout the year. Historical typhoon record shows that over than 60% of typhoons strike Taiwan from east to west, crossing the Kuroshio path. Because of this, the region is ideal for studying ocean-atmosphere interactions. And why we study typhoon Kuroshio interactions and why this is important. The upper ocean thermal structures strongly influence tropical cyclone intensity. Strong winds during the typhoon can disrupt ocean circulation, such as the Kuroshio. However, due to limited observations during the extreme weather event, how typhoon affect the Kuroshio is still not fully understood. There are the goals of the study. First, to investigate how the Kuroshio responds to Typhoon Morakot. Second, to examine whether the strength and path change during the typhoon. Third, to analyze the physical mechanism behind typhoon Kuroshio interactions. Next is the background of typhoon event. Typhoon Morakot formed on August 3, 2009 in the western North Pacific, then moved westward toward Taiwan and eventually passed over Taiwan on August 7 to 8. To study this event, we use several types of observational data. First, Argo drifters were used to measure surface current velocity. Second, Argo float provide vertical temperature profiles of the upper ocean. Third, satellite wind data provide wind fields. In addition to observations, this study also used an ocean model called Regional Oceanic Modeling System. This is a three-dimensional equation ocean model used to simulate ocean circulation and sea surface dynamics. Initial conditions were taken from the HICOM and ENCODA data assimilation system. Before analyzing the result, the model performance must be verified. This picture shows the compare simulated current with Argo drifter observations. The color map shows the simulated current speed. The color closer to red indicates stronger current. The dot represents the drifter position, and their color follow the same color bar to indicate the observed current speed. We can see the simulated current generally match Argo drifter data. The correlation coefficient is about 0.7, indicating that the model results are reasonably reliable. One of the major results of the Kuroshio mainstream, study is the Kuroshio mainstream shift eastward during the typhoon. This picture shows the evolution of Kuroshio mainstream by model. The x-axis is the longitude and the y-axis is the latitude. The gray line is the path without Morakot, while the dashed line is with Morakot effect. We can see before the typhoon impact, the Kuroshio remained stable. When the typhoon approached at latitude 24 degrees north, the current shifted more than 1.5 degrees eastward. And this shift reached a maximum when the typhoon center was about 100 kilometers from the Kuroshio. And after the typhoon passed, the Kuroshio returned to its normal path. Another phenomenon observed is temporary shutdown of the Kuroshio flow. This picture shows the evolution of the Kuroshio intensity during the typhoon by model. The x-axis is the current speed and the y-axis is the latitude. The gray line is without Morakot effect, while the dashed line is with Morakot. We can see when typhoon approached, the northward flow nearly stopped for about 6 hours. As the typhoon moved closer and passed, the current suddenly intensified in the north. This phenomenon is called Kuroshio intermittency. Now I will explain the mechanism behind the Kuroshio intermittency. This is the normal Kuroshio. And when a typhoon comes, the strong northerly wind blocks the northward flow and causes the water to accumulate upstream. As the typhoon moves westward, the northerly wind also moves westward, causing the Kuroshio to temporarily shift eastward. And after the typhoon passed, the blocked water is released and the flow rapidly accelerates downstream. The typhoon also caused sea surface cooling. This figure shows the sea surface temperature by model. The red indicates higher temperature and the blue indicates lower temperature. And we can see a cool offshore jet formed east of Taiwan, and the sea surface temperature dropped significantly. The cooling extends northward along the Kuroshio, with temperature about 4 to 5 degrees colder than surroundings. This figure also shows the upper ocean cooling observed by Argo float. The x-axis is temperature and the y-axis is depth. The solid line represents the temperature during the typhoon, and the dot and dashed line represent the before and after. We can clearly see that the temperature dropped by about 4 degrees near the surface during the typhoon. In addition, the gray line shows the model results, which are consistent with Argo observations. And this cooling was mainly caused by the strong wind during the typhoon. This is the y-axis is the wind speed. This figure shows the wind field in the region of the cooling occurred. And this gray line shows marks the time of typhoon passed over the Kuroshio. In this period, we can see strong westerly wind was observed, and this wind enhanced vertical mixing and upwelling, bringing the cold water to the surface. After the typhoon passed, the wind turned southwesterly and helping to generate an offshore cool jet. In conclusion, this study shows that Typhoon Morakot strongly modified the Kuroshio. The Kuroshio experienced temporary intermittency, shift eastward, and weakened. Another important result is ocean feedback may influence typhoon intensity. The offshore cool jet reduce sea surface temperature and then decrease heat flux to the atmosphere. This provides a negative feedback to the typhoon. Thanks for your listening.